One way to solve this is to use so-called indirect pointers. Here is an inode structure that uses these indirect pointers. Just like before, the inode contains metadata and pointers to blocks of data. The inode is organized in a way that first it has all of the metadata, owner, when is the file last accessed. Then it starts with the pointers to blocks. The first part is a list of pointers that directly point to a block on disk that stores the file data. Using the same example like before, where we had blocks that are 1 kilobyte large and we use 4 bytes to address an individual block, these direct pointers will point to 1 kilobyte of data per entry. To extend the number of disk blocks that can be addressed via a single inode element, while also keeping the size of the inode small, we use so-called indirect pointers. An indirect pointer, as opposed to pointing to an actual data block, will point to a block that's full of pointers. Given that our blocks are 1 kilobyte large and our pointers are 4 byte large, that means that a single indirect pointer can point to 256 kilobytes of file content. So just using a single element of the inode data structure as this indirect pointer can significantly increase the overall size of the files that can be supported in this file system. Now, if we need even larger files, we can use double indirect pointers. A double indirect pointer points to a block which contains pointers to blocks of data. If every block has 256 pointers, then this double indirect pointer can help us address 256 times 256 times 1 kilobyte blocks for a total of 64 megabytes of data. We can apply the same idea to triple indirect addressing and so forth. The benefits of using indirect pointers is that it allows us to continue using relatively small inodes while at the same time addressing really large files. The downside is that this has an implication on slowing down the file access. With direct pointer, when we need to perform an access to a portion of the file, we need to first access the inode itself, and that may be stored somewhere on disk. And then we will find out what is the pointer to a particular data block, and we will access the data block. So we may end up performing 2 disk accesses per file access, and that's at most. With double indirect pointers, the situation is very different. We need 1 disk access to get to the block that contains the inode. Then we may need another disk access to get to the first addressing block. Then from there, a second disk access to get to the second level addressing block. And then finally, we get to the block that contains the data. So for a single file operation, we may end up performing up to 4 disk accesses. That's a 2x performance degradation.